Hi everyone, this is my final project presentation for Geography 883. The purpose of my final project is to analyze the land cover change of the Eagle Rock Resort and Humboldt Industrial Park over a 15-year period to determine the loss of forest. The land was primarily forested mountains and hills, but these two growing development projects have significantly altered the landscape. As a secondary objective, three different classification methods were used to compare the performance. I wanted to compare the accuracy of each method to determine if a quicker method like unsupervised classification made more sense for a project like this, or if favoring a more manually intensive method like object-based image analysis in eCognition or ArcGIS Pro is worthwhile. The study area for this project is located in Hazel Township, Pennsylvania, shown here in the red box in relation to the state of Pennsylvania. Here is a more localized view with the area of interest shown in the red box. This is in relation to Hazleton, Pennsylvania and Interstate 81. Eagle Rock Golf Course and Humboldt Industrial Park are labeled on the base map. Both development projects intersect the project area but are not completely contained within its boundary. And finally, here is the area of interest at a local level. The area was chosen because the north section of Eagle Rock, starting north of the golf course in the central part of the area of interest, and the southwest portion of the Humboldt Industrial Park are both the newest additions in each development project. The three data sources I used for this project include NAPE imagery from 2004 and 2019, as well as LiDAR data collected as part of the PA Map LiDAR project that covers the area of interest. Here is a screenshot of the 2004 NAPE imagery taken with a color infrared imagery sensor. The three-band imagery was captured on June 12, 2004, and shown here overlaid on the Esri topographic base map. It is in the 1-2-3 combination, which is near infrared, red, and green. The coordinate system is in NAD83 UTM zone 18 north in meters. It has a 1 meter pixel resolution and an 8-bit radiometric resolution. The company that captured this imagery is called Suredex. I downloaded this from USGS Earth Explorer. And here's a screenshot of the 2019 NAPE imagery taken with a near-color infrared imagery sensor. The 4-band imagery was captured on August 5, 2019, and shown here overlaid on the Esri topographic base map in the 1-2-3 natural color combination. The coordinate system is in NAD83 UTM zone 18 north in meters. It has a 0.6 meter pixel resolution and an 8-bit radiometric resolution. This was also downloaded from USGS's Earth Explorer. I downloaded the PA Map LiDAR data directly from their web application, which provides the data in LAS format. The PA Map LiDAR program has extensive metadata that helps us understand the specifications of the collection. The LiDAR data was captured for the PA Map project by BAE Systems with several contractors. Hazel Township is located in Luzerne County, which is the isolated example of 2006 data in eastern Pennsylvania. The coordinate system of the data is in EPSG code 2271, which is NAD83 State Plane, Pennsylvania North in US feet. This dataset also has a defined vertical coordinate system of NAVD88 in geoid 3. The project was collected with LiDAR quality 3, meaning it has a nominal average point spacing of 1.4 meters with a vertical error RMSE of 20 centimeters. The two primary softwares I use for this project are ArcGIS Pro and eCognition. ArcGIS Pro is used for the unsupervised classification and random trees classification based on supervised training samples. It was also used for calculating total acreage for each land type and for the thematic mapping accuracy analysis. eCognition was used for the object-based image analysis. In addition, Microsoft Excel was used extensively for recording observations and calculating error matrices. Here is my workflow overview, including data preparation, followed by the three different classifications. At the end of each classification, the total acreage for both 2004 and 2019 imagery are calculated and compared. As a final step, I perform thematic accuracy assessments on each of the three methods. There were several pre-processing steps in ArcGIS Pro needed to prepare the imagery and LiDAR for use in the analysis. The first step was to create a mosaic dataset in ArcGIS Pro for the NAPE imagery downloads. The area of interest intersected with multiple tiles, so creating a mosaic dataset was necessary to combine them. After creating the mosaic dataset, the area of interest boundary was used to clip the imagery. To use the LiDAR data, a DEM and DSM were created. The DEM was then subtracted from the DSM to create the NDSM raster. As a final step, the NDSM raster was clipped to the area of interest and projected into the same coordinate system as the NAPE imagery. For the simplest classification method, ISOCluster unsupervised was run in ArcGIS Pro with a total of 10 classes, a minimum of 10 for class size, and 10 for the sample interval. This creates a simple classification that needs to be assigned to its corresponding land class. For this project, I was interested in collecting 5 land use categories: buildings, grass, trees, water, and pavement. I grouped both streets and pavement together as the purpose of this project is to look at deforestation. The type of impervious surface is not as important. Here is an example of one of the outputs after reclassifying to the proper land use. It will be discussed further in the results, but it's very generalized and clearly messy between grass in light green and trees in dark green. For supervised classification, I first segmented the data. For the 2019 imagery, I used 20 for spectral detail and spatial detail since I wanted to over-segment to limit object bleed. For the 2004 imagery, I experimented with a few different segmentations, but ultimately decided to go with 15 for spatial detail and 15 for spectral detail because the difference wasn't that strong, and the lower details seemed to group the noise in the imagery from clouds into larger chunks, which I will get into later on in the presentation. I made sure to collect at least 30 samples for each of my 5 land use types during my training data collection. I used random trees classification because it is more effective at picking up impervious surfaces like buildings than support vector machine. Random trees misclassify shadows as water, but again, keeping in mind the purpose of the project, I wanted to make sure that impervious surfaces and trees were collected the most accurately. Here's an example of one of the outputs after the random forest classification. You can see the roads and buildings are well defined. For the final classification in eCognition, I performed 3 different classifications, one for the 2004 imagery with the NDSM, one without the NDSM, and one with the 2019 imagery. The LiDAR data used to create the NDSM was 2 years newer than the 2004 imagery, so I wanted to make sure there weren't any drastic changes. This process tree is for the 2004 imagery without the NDSM. The segmentation was performed using spectral difference with a quad tree scale of 20, a multi-segmentation region grow scale of 20, and a maximum spectral difference of 10. Also of note, the shape and compactness were both set at 0.5 to keep color and shape evenly impacting the results of the segmentation. During the classification process, I focused on separating vegetation using NDVI. The remaining rule sets were based on mean spectral characteristics. I also experimented with GLCM homogeneity and contrast of the red band to see if it made any impacts compared to the near-infrared band we experimented with throughout this course. It did provide some value when trying to separate pavement from buildings. Here's the process tree used for the 2004 imagery with the NDSM. This process tree incorporates the NDSM to try and separate grass from trees and buildings from pavement. The spectral difference segmentation is the same as the previous classification. And finally, here is the process tree for the 2019 NAPE imagery. Like the process tree for the 2004 imagery, it focuses on the NDVI values to try and separate vegetation from impervious surfaces. Calculating acreage for each of the classified outputs depended on the method. The first 2 classification methods outputted rasters, so calculating acreage needed to be done by considering pixel size. The 2004 imagery was 1 meter pixel resolution, while the 2019 imagery was 0.6, an important distinction to consider during calculation. The eCognition outputs were in the form of a shapefile, so using the Calculate by Geometry function in ArcGIS Pro was an easy way to find those areas. In order to assess the accuracy of the segmentations, I used ArcGIS Pro to calculate accuracy assessment points. I used equalized stratified random with 50 points per class. I reviewed each of the points, though it took a very long time to review 250 points for each of the 7 classifications that I did. The confusion matrix was placed into an Excel spreadsheet. The results of the unsupervised classification are shown here. Visually, we can see the new development in the north part of the 2019 imagery, and we can see a few new warehouses in the south section. It appears that there are some irregular buildings at the top of the 2004 imagery and some lakes that have been removed. The land cover change from 2004 to 2019 can be shown here in this table. The results show a reduction in buildings, pavement, and trees, with an increase in water and grass. Some of these results make sense, including the increase in grass for cleared lots and the decrease in forest for new development. However, the impervious surfaces and water reduction doesn't seem quite right. The accuracy assessment supports the fact that the land use classes were not entirely correct. There was only a 50% overall accuracy with the unsupervised 2004 classification. Buildings and water performed particularly poorly in the user's accuracy. The 2019 accuracy assessment was slightly better, but water in particular remained a huge problem in the unsupervised results. The results of the supervised classification are shown here. Visually, we can see classification appears cleaner than the unsupervised classification. Pavement appears more evenly defined in this method. The land cover change from 2004 to 2019 based on the random trees supervised classification shows a more expected land cover change percentage. It shows a reduction in pavement and trees with an increase in water, grass, and buildings. Some of these results make sense, including the increase in grass for cleared lots and the decrease in forest for new development, along with the increase in buildings for new warehouses. However, the pavement reduction and water increase still don't quite add up. For the 2004 accuracy assessment, the land classification had an increase to 61% compared to the 50% for unsupervised. Buildings performed better, but pavement and water had poor producers and users accuracy, respectively. The 2019 supervised classification accuracy results showed an identical overall accuracy to 2004. Pavement saw a large increase in accuracy, but water continued to be a problem. The results of the e-cognition classification are shown here. At a high scale, it actually appears like the data is less defined and clean than the supervised classification in ArcGIS Pro. However, a lot of this is due to the unclassified objects. This is the results of the 2004 and 2019 object-based classifications without NDSM. And here are the results of the 2004 land use using the NDSM and the 2019 results. The land cover change from 2004 to 2019 based on the object-based classification and e-cognition with NDSM shows an expected land cover change. It shows a reduction in trees but an increase in grass and pavement. Buildings and water stay constant. The results without the NDSM are different, with a reduction in pavement but slight increase in buildings. For the 2004 accuracy assessment, the land classification accuracy was lower than what was found in the ArcGIS Pro supervised classification. Buildings and water remained a problem, with pavement also showing poor results in the producer's accuracy. Factoring in NDSM, the results had a slight uptick to 60% for overall accuracy. However, much of the same categories that plague the accuracy without NDSM are still present here. The results of the 2019 e-cognition classification yielded the highest results of any accuracy assessment, with 64% overall accuracy. One of the biggest challenges I had with this project was the quality of the imagery. While the NAPE data is higher resolution than sources like Landsat, the 2004 color infrared imagery was a major challenge. It had clouds and other artifacts. Many of the classification problems can be explained by the 2004 imagery. There are clouds in the northwest corner circled in black, shadows from clouds circled in blue, and strip mines circled in red, which do not fall into any of the 5 categories chosen for this analysis. In hindsight, I should have created another class for bare soil to account for rocky areas and former mines. Either way, working with the nearly 7,500 acre area of interest was difficult to try and solve all these problems. Another huge challenge throughout this project has been shadows. The forested nature of the developed area makes it difficult to accurately class pavement, especially when the shadowed areas closely resemble the spectral characteristics of water. I was, however, pleased with the results of grass and forest throughout the exercises. At the end of the day, I felt my results somewhat reflected what I expected. I expected a small increase in buildings, an increase in pavement, an increase in grass, with a reduction in trees. Despite their challenges, each of the methods showed that the trees were ultimately reduced, ranging from 1,056 acres to 619 acres of cleared forest. Thinking back to the research question, this was ultimately what I wanted to find out. I also found that there is a clear distinction in results from unsupervised to supervised classification. This was expected, but important to prove. Where I would like to conduct further research is whether e-cognition, object observation, and process tree is more effective than training sample manager in ArcGIS Pro. The accuracy results don't show a large increase from random trees to e-cognition, though e-cognition took at least 2 to 3 times longer to conduct the analysis. This is also only a sample size of 1. I was also impressed with NDSM and its ability to help classify trees and buildings. It also helped with things like shadows from clouds. However, it reinforced the idea that the data should be the same vintage because there were several instances of misclassification due to mistakes in the NDSM. The most important thing I learned during this project was the importance of scale. Visually interpreting results over a large area may look promising, but digging into a local level may show that the results are not as strong, or vice versa. In this case, looking at the results and the highest overall accuracy of 2019 imagery classified with eCognition, the global scale looks messy with lots of unclassified areas, but when I zoom in, I see decent results, with most of the unclassified areas consisting of shadows. Thanks everyone for listening to my final project presentation. Again, I'm appreciative of your feedback and open to answering any questions. Have a great rest of your year.